Hello student, how are you? I hope all of you are well and doing good. So today is the machine tool lecture number 2, right? This is the 19th lecture, and today we are going to cover the remaining part of the lathe and we are going to start drilling, right? So let me start. See here. Now I'm going to discuss work holding device, right, in lathe. Work holding device in lathe, right? Work holding device in lathe. So work holding device in lathe, right? Number one work holding device is your chuck, right? That is a three jaw chuck. Okay, three jaw chuck, three jaw chuck, three jaw chuck, right? Three jaw chuck. Three jaw chuck basically you can say it's a self-centering chuck. Three jaw self-centering chuck. Three jaw self-centering chuck. Three jaw self-centering chuck, right? Three jaw self-centering chuck. Three jaw self-centering chuck, right? Three jaw self-centering chuck basically used to hold the job which are of disc type, right? Which are of disc type. So disc type job, disc type job, okay, held, okay, in three jaw chuck, okay, three disc type jobs being held, right? Jobs being held, right? Now number two, now number two here, see, number two here, your four jaw chuck, right? Four jaw chuck, four jaw chuck, CHUCK, four jaw chuck. My dear, in four jaw chuck, right? In four jaw chuck, basically, this is an independently adjustable chuck, independently adjustable chuck, four jaw chuck, or you can say it is what, four jaw independently adjustable chuck, four jaw independently independently, right? Independently adjusted chuck, adjusted chuck, right? Independently adjusted chuck, right? Independently adjusted chuck. Is it clear? Four jaw independently adjustable chuck. So all the jaws are what? Adjustable. So here you can held, here you can held disc type job, disc type, or axial symmetrical job, axial symmetrical job, symmetrical, right, job, okay, or prismatic job, prismatic job, prismatic jobs you can hold. Even a little bit complex type of workpiece you can hold here, right? A little bit complex type of workpiece you can hold here, right, my dear? So number three. So let me explain you. Okay, so these are the three jaw chuck, and this is what, four jaw chuck, right? Now my dear, let me tell you the collet. Okay, collet, 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 collet. In collet, collet basically hold a small cylindrical job, right? collet basically, okay, right? So collet here, generally we use a collet. Collet generally used to hold a cylindrical rod-like job, cylindrical, cylinder, cylindrical rod-like job, right? Cylindrical rod-like jobs being held in, okay, in collet. Now the next is your fourth one, that is for magnetic chuck. Magnetic chuck. My dear, in magnetic chuck, basically a workpiece which are cylindrical or which are disc type, right? Which are disc type but has a very small length, has a very small length. Those type of workpiece are going to be held on a magnetic chuck. So let me write down for a thin job, for for thin job, okay, thin disc type job, for thin disc type job, right? Even you can hold a thin job also, but disc type job is more preferable, right? Even it can hold a any thin job, right? Next is, my dear, the next is what? The next is your collet or your mandrel, right? Mandrel. A hollow type of workpiece is going to be held, okay, on mandrel, a hollow workpiece, right? Hollow workpiece is going to held in a mandrel, right? In a mandrel. So I hope this point is crystal clear. Now let's move to the next slide. Now let me talk about the other work holding device, that is a face plate. Next is your face plate. Next is the face plate, right? This is what, fifth, and this is sixth, and this is face plate, right? Face plate. Now face plate basically is what? Generally a job which is a complex shape, okay, a job which is a complex shape or a odd shape which is not able to hold which are not able to hold in any other, right, in any other work holding device. They can be adjusted on the face plate, they can be held on the face plate. So face plate basically face plate basically for odd shape jobs, odd shape jobs, right? Odd shape jobs being held in a face plate, being held in a face plate, being held in a face plate, okay, being held in a face plate. Is that right? Is that clear? Now next is what? Seven. Seventh. Seventh. There will be a lathe centers, right? There will be a lathe centers, right? There will be a lathe center. Generally lathe centers, like there will be a live lathe centers look like this. See, it will be look like this. Let me draw the lathe center. Let me draw the lathe center. These are the lathe center, right? These are the lathe center. Okay. The center which is going to held at the headstock side is known as live center. Light live center, right? Live center. The center the center which is held at the tailstock side is known as dead center, right? Dead center. Okay, a cylindrical type of job is going to be held, right? Is going to be held in the center, my dear, right? Now there will be a lathe dog. There will be another work holding device which is known as lathe dog. 8. Lathe dog, right? Lathe dog. Generally, lathe dog is combinedly used with the faceplate. Lathe dog is combinedly used with the faceplate and lathe center. Okay, to give the rigidity to the workpiece. To give the rigidity to the workpiece. Am I clear? To give the rigidity to the workpiece, right? To give the rigidity to the workpiece. The next is your wrist. Your wrists, that is 9, RESTS, rest. Basically, rest generally used to support the workpiece while machining. Rests are of two types. Rests are of two types. One is steady and the another is follower. Okay, rests basically are of two type, my dear. Rests basically are of two type. One is steady and other is follower, right? And other is follower. So these are the work holding device which we generally use in the lathe. Now let me calculate the machining time. Machining time calculation. Let me discuss machining time calculation, right, in lathe while turning, right, while turning. Now my dear, there is a workpiece, right? This is a workpiece and we are doing a turning operation. See here, see here, see here. This is a workpiece and this is my tool, right? This is my tool. Here you can see this is the tool, right? This is the tool. This is the tool, right? This is the tool. Now the tool is moving. You are giving the feed to the tool, right? You are giving the feed to the tool, and this is axis of rotation. This is axis of rotation. And suppose that initially, my dear, the workpiece is like this. This is the workpiece, right? This is the workpiece, right? And we are moving the tool. We are moving the tool like this from here, right? This is the movement of the tool. Here you can see, right? This is the approach distance. Let's say this is what? This is the approach distance, right? And this diameter, this is the initial diameter, right? This is the initial diameter. Let's say it is D1. This is the final diameter which is produced, D2. This is the approach distance, and let's say this is the machining length, right? This is the machining length. Let's say small l, okay, and let's say this is the over travel distance, right? This is what? Over travel distance O. So the total length of machining. So here the total length of machining is what? The total length of machining. Total length of machining. Total length of machining, okay, is what? Let's say capital L, and it will be approach length small l plus O, right? So this is the total length of machining. Okay, this is the total length of machining. This is what? This is the total length of machining. Okay, So here the workpiece is rotating. Here workpiece is rotating with RPM what? N, that is revolution per minute, right? So and here F is what? F is a feet, that will be in mm per revolution, right? Mm per revolution. So here the tool velocity, let's say it is Vy, it will be what? F into N, and it will be in mm per minute. Am I clear? This is the tool velocity. So machining time, right? Let's say Tm equal to what? Equal to capital L divided by your Vy, that is approach plus machining plus over travel divided by F into N, right? So it will become in minute, right? It will become in minute. So this point is clear. Now, my dear, cutting velocity, right? Cutting velocity. Now, there is another parameter which is known as cutting velocity. Cutting velocity, right? Cutting velocity, and let's say V, and it is pi d1 initial diameter RPM, because diameter generally will be in mm, right? Generally will be in mm. So pi d1 n divided by 1000 meter per minute, right? Meter per minute. Now here, let's say, now here, this is a cutting velocity. Is that clear? Now, my dear, here, please see cutting velocity, right? Now, material removal rate. If you want to find material removal rate, then pi, okay, pi by 4 d1 square minus d2 square into f into n. So that will be in mm cube per minute, right? Mm cube per minute. Now here you can see that there will be a depth of cut. This is what? This is the depth of cut, that is small d, right? That is the small d depth of cut, right? Depth of cut. So see here, d, depth of cut, depth of cut, that is small d equal to what? d1 minus d2 divided by 2, right? d2 divided by 2. So this is depth of cut. So I hope this point are crystal clear to everybody. Any doubt regarding this? Any doubt? Everybody, is there any doubt? Yes or no? Okay, let me solve a question, right? Let me solve a question so that the point will be crystal clear to you people, right? So that the point will be crystal clear to you people. Okay, now see here question. This is a question. How much machining time? How much machining time? How much machining time will be required? Will be required to, okay, reduce the diameter of, reduce the diameter of, okay, reduce the diameter of a cast iron, okay, cast iron rod from 120 mm, right? 120 mm to 120 mm to 120 mm to 116 mm, right? 116 mm over a length of, over a length of 100 meter or 100 mm is 100 mm, right? 100 mm by turning using, by turning using, okay, using what? Using a carbide, using a carbide tool, let's say, okay, carbide tool. Now, cutting velocity is here, cutting velocity, cutting velocity, it is given that cutting velocity is what? Is 100 meter per minute, is 100 meter per minute. Cutting velocity is what? 100 meter per minute, and feed rate is, and feed rate is also given, and feed rate is what? Feed rate is 0.2 mm per revolution. We want to calculate the machining time, right? We have to calculate the machining time. So machining time, diameter initial is given, final is given over a length of 100 mm. Okay, using a carbide, cutting velocity is given. My dear, for the machine, for the solution, right? For the solution, solution. See the solution. Here, machining time equal to what? Total length divided by your tool velocity. Total length is what? 100, right? 100. It will be in mm, and it is F into N, right? And it will be mm per minute, mm per minute. So overall, the unit will be in minute, right? So overall, the thing will be in what? That will be 100 divided by feet is given, that is 0.2, but n is not given, so it will be comes in minute, right? So we have to find out what? N, am I right? So here the cutting velocity is pi dn, pi d1n divided by 1000, because we are cutting the initial diameter, right? Meter per minute. And here cutting velocity is given, the cutting velocity is 100 meter per minute. So let me put here 100, right? 100. So here you will get, so 100 equal to pi d1 120 into n divide by 1000. So here you will get the answer 100 into 1000 divide by shift pi into 120. So here you will get n equal to 265.25 revolution per minute, right? So machining time will be what? 100 divided by feet, that is 0.2 into 265.25, right? Minute. So answer will be 100 divided by 0.2 into answer 1.88 minute. So this is the machining time calculation. I hope the point is crystal clear, right? I hope the point is crystal clear, right? Uh, Let me discuss one more question here. Let me discuss one more question. A very good question of GATE exam. A very good question of GATE exam. A very good question of GATE exam. See here. Question. See. A disc of 200 mm outer diameter. A disc of 200 mm, right? Outer, outer, and 80 mm inner diameter. 80 mm inner diameter is faced off, is faced off right? By how much feet is phased of 0.1 mm per revolution. 0.1 mm per revolution, right? Per revolution. With depth of cut, with depth of cut, with depth of cut, how much? With depth of cut of 1 mm. With depth of cut 1 mm, right? With depth of cut of 1 mm. The facing operation is undertaken. The facing operation, the facing operation is undertaken. The facing operation is undertaken at a constant cutting speed of at a constant at a constant cutting speed of cutting speed of what? At a constant cutting speed of 90 cutting speed of 90 meters per minute, right? In a CNC lathe, in a CNC lathe, right? In a CNC lathe. So machining time. Calculate the machining time. Calculate the machining time. Calculate the machining time. Right. Calculate the machining time. We have to neglect assuming, 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 assuming that approach and over travel, approach, approach and over travel and over travel length of tool negligible, length of tool negligible, right? So this is the solution, right? This is the solution. So here is the solution, my dear. What is the solution? Basically, this is a very good question. This is a very good question. Here, see, see here, a disk. This is a disk. See, this is a disk. See, this is a disk. Now, here, this is a tool. This is a tool. Now, this is a diameter. This is a diameter. Okay, 200 mm. The next diameter is this 80 mm. Is phased off. This is a feet 0.1 mm per revolution with a depth of cut 1 mm. The facing operation undertaken at a constant cutting speed. Now it is given that constant facing operation, there is a constant cutting speed, constant cutting speed, that is V, and okay, you know that V equal to, right, here V, constant cutting speed, this is 90 meter per minute. My dear, let me tell you one thing. When your tool is moving, suppose that when the tool will reach here, suppose that when tool will reach here, cutting velocity is going to be very, let me clear you very clearly. The tool velocity is going to change, right? The tool velocity is going to change. Here, see, here, see, right? Here, see, here, see, here, see. Here the tool velocity is going to change, right? Is going to change, right? Because we know that V, we know that cutting velocity is pi dn divided by 1000, right? Divide by 1000, and it will be meter per minute. As you can see from the figure, as the diameter get changes, as the diameter get changes, right? Here you can see diameter get changes, the cutting velocity is also going to be changes. The cutting velocity is also going to be changes, right? Here v is also going to be what? Changes. So, my dear, so what will be the diameter actually? That's why he's saying that the cutting speed is what? Constant, right? That the cutting speed is what? Constant. So basically we are taking constant velocity, that is the average velocity. That is what? Average velocity. We are taking the average of this. We are taking the average of this, that is the v constant, and that is that is what? That is your 90 meter per minute, right? My dear, it means your V average basically comes when you are taking D average. When you are taking D average and divide by 1000 meter per minute. Am I clear? Is that point is clear? Yes or no? I hope this point is clear. Now, please see. Now, please see. Here D average is what? D average is very simple. D average is your 200 plus 80 divided by 2, that is 140 mm, right? 280 plus 80, 280 divided by 2, that is 140. So you will get n, right? From here you will get n. So n will be, that is 90 into 1000 divided by pi into 140 rpm, revolution per minute. So let me see. Shift pi into 140. So here RPM will become 204.62 revolution per minute, right? Revolution per minute. Now here, see here. Now you have the RPM now. So now the machining time will be what? Machining length divided by f into n. So machining length will be what? This much is the machining length, yes or no? This much is the machining length, if I am not wrong. This much is the machining length L, and this is 100 minus 40, that is 60. So here this is what? 60. Here you can say this is a 60 mm from the figure. Divide by feed, and feed is what? You can see that is the feed is feed is 0.1, right? Feed is what? 0.1, and into rpm is what? 204.62, right? 0.62, it will becomes in minutes. So 60 divided by 0.1 into 204. Okay, so here the answer will be 2.93, okay, minute. So here the fishing operation time is large, it means speed is very less. That's why you are getting a very less time here. That's why you are getting a very less time here, my dear. I hope this point is crystal clear, right? I hope this point is what? Crystal clear. Now let's talk about the errors in tool setting, right? Let's talk about the errors in tool setting. Let's talk about the error in tool setting. See here. Let's talk about the errors in tool setting, right? Errors in tool setting, right? Errors in tool setting. Tool settings. Errors in tool settings. My dear, errors in tool setting is what? Basically, suppose we are doing a turning operation. Now you can see the cross-sectional view, right? And here, please see, right? See, right? Now, suppose that generally the tool will be at this position. Are you getting my point? Tool will be at this position. Please see. Generally, you have seen that generally the tool will be at that position, right? So, the effective rake surface or the effective rake angle is what? This is rake angle, and this is tangential, and this is what? Relief angle. This is rake angle and relief angle. My dear, suppose that if you are going to offset, right? If you are going to offset, let's say you are going to offset the tool here. You are going to offset the tool like at here, right? If you are going to offset the tool like here, then what will be the effective rake angle and clearance angle? My dear, for that you have to connect the tip of the tool, okay, the tip of the tool at the center of the workpiece. Now this is a reference line, again a line which is perpendicular, right? A line which is perpendicular to the reference line, and see here the rake angle get increases, right? Alpha dash, and here relief angle get decreases, okay? So if you offset the tool by theta, then how much will be the rake angle? That is initial rake angle plus theta. The effective relief angle which get reduces how much? The relief angle, initial relief angle minus theta, if you are going to offset the tool above. Similarly, if you are going to offset the tool, right, if you are going to offset the tool by this manner, please see here, see 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 here, if you are going to offset the tool by an amount theta, then the rake angle get decreases alpha dash, but here the reference, but here the relief angle get increased. How much rake angle decreases? Alpha minus theta. How much relief angle increases? Initial plus theta. So please remember this point, right? So please remember this point, right? Please remember this point in a very well manner, right? Now let me discuss the type of lathe. Okay, there will be a turret lathe, okay, and there will be a capsican lathe. Okay, there will be a turret lathe and there will be a capsican lathe. So turret lathe and capsican lathe, see here, turret lathe, right, and capsican lathe, okay, and or just a minute, let me write down capsican lathe first. Capstan lathe, capstan lathe and turret lathe, right, and turret lathe. See, see the difference. See the difference, right? See the difference. See the difference. See here, point number one. See here the point number one. Capsican lathe is short slide, right? Short slide. While the turret lathe is Okay, large size. There will be a slide is large. Capsican lathe. In capsican lathe, there will be a short slide, right? Since the saddle is since the saddle is what? Saddle is clamped on the bed. Clamped on the bed. Clamped on the bed in position. Right? Bed in position. Bed in position. Point number while in the turret lathe, saddle moved along the bed. Here saddle is not fixed. Saddle moved along the bed. Now let imagine if saddle can move along the bed, so you can move the turret. So there is a large space now, thus allowing the turret to be thus allowing thus allowing the turret to be the turret to be of large, okay, turret to be of large size, of large size, right? Now point number 2, light duty machine. It is what? Light duty machine, right? Point number 2 here, it is heavy duty machine. It is heavy duty machine, my dear, right? It is what? It is a heavy duty machine. Is that clear? It is a heavy duty machine. Now in turret there is an indexing mechanism, right? The hexagonal turret, there are turret, basically turret, there will be a turret now where you can mount the tool. That turret is going to rotate by Geneva mechanism. By Geneva mechanism. Is that clear? By Geneva mechanism. Okay, by Geneva mechanism. Okay. So that's it for the lathe, right? So tomorrow we are going to discuss, okay, drill. Tomorrow we are going to discuss drill. Let me tell you, tomorrow we are going to discuss drill, right? Tomorrow we are going to discuss drill. What we are going to discuss in drill? Like geometry, okay, B, machining time, machining time, in where? In blind hole, in where? In throw hole, throw hole. Okay, we are also going to discuss here what will be your approach, or what will be the cone height. So these things we are going to discuss. Let me give you a brief idea. Basically, let's say if you are doing a drilling operation, right? If you are doing a drilling operation, see here, if we are doing a drilling operation here, see, this is the workpiece which you are going to drill. See, now the hole is going to be drilled. Now two conditions may be possible. The condition one, either the hole will be blind, right? If the hole is blind, my dear, like this is a blind hole. Or it might be possible that the hole, this is what? This is a blind hole, right? This is blind hole, right? This is blind hole. Now blind hole means we are not going through the complete height. You can see here, right? You can see here we are not going to the through height. You can see here, right? You can see here. Okay, now tell me, this is the drilling axis. This is the drilling axis, right? This is a drilling axis. This is a drilling axis, right? This is a drilling axis. My dear, if this is a drill tool, if this is the drill tool, okay, now tell me, up to which surface? Or just a minute, just a minute. Here, let's say this is a drill tool, right? Let's say this is a drill tool. Now it is moving from here. Now, my dear, if it move from here to make this hole, the drill tool has to move up to at least this height. Then you can move this much of cylindrical. This much is the height of the cylindrical hole basically. This much is the height of what? Cylindrical, okay, hole. That is, let's say L1. But to make this hole, the tool has to move at least, okay, the tool has to move this this extra height, okay, this extra height. This is what? L3, that is a cone height, and we will discuss what is L3. L3 is nothing, it is a cone height, right? And the another type of tool, like when you are doing, my dear, let's say when you are doing, see, a throw hole, right? When you are doing a throw hole, right? When you are doing a throw hole, see here, when you are doing a throw hole, when you are doing a throw hole, see, when you are doing a throw hole like this, right? Like this. So in that case, the drill tool has to move. My dear, the drill tool has to move. See here, the drill tool has to move from here to here. This is the complete machining height. This is the complete machining height, right? This is a complete machining height. So basically this is nothing, it is a throw hole. It is what? It is a throw hole. It is a throw hole, right? It is what? It is a throw hole which you are going to produce, right? A throw hole which we are going to produce. So that will be the machining height in drilling that we are going to discuss in tomorrow's session. So thank you very much for watching this video. We are going to meet tomorrow. Thank you.